They told him to open it and understand it. Ober engineer Carl Schmidt expected to find a hastily cobbled machine, cheap materials, shoddy craft, the kind of object an army could afford to lose. Instead, beneath a swinging lamp in a makeshift workshop near Anzio on March 18, 1944, he uncovered a different kind of design thinking. Not refinement for its own sake, but a deliberate, forgiving practicality that pointed away from the vehicle itself and toward something larger. That discovery is the axis of this story. German engineers opened a half-track and found America's secret. The field kitchen had been pushed aside to make room for the vehicle. Men in greasy overalls moved like constellations around the metal frame, boots on gravel, breath in the cold air. The half-track sat ugly and utilitarian in the mud, its rear track slack, the front wheels capped in dust. A single bare bulb hung from a branch and threw hard light across stamped fenders, revealing rough welds and tool marks. Schmidt crouched and pried open the engine hatch. The smell was oil and dust, a human smell of diesel and hands that had been working in the dirt. Schmidt was not an ideologue. He had been trained in precise German workshops, Daimler factories where measurements and tolerances were measured like the pulse of a machine. He had an engineer's habit of noticing things that others passed by, a bolt head with a nick, the angle of a bracket, the way a spring was anchored. He knew what masterpieces of engineering looked like when they were meant to last, to be maintained by skilled mechanics using careful procedures. He expected the half-track to be the opposite, hurried, fragile, disposable. What he found instead was intentional generosity, parts that did not demand finesse so much as they demanded supply. The first obvious detail was the access. Panels and fastenings were oversized, often only hand-friendly. Bolts were nothing like the precise hex socket Schmidt preferred. These were larger, looser and fit, with heads sculpted for quick grip. Castings and stampings dominated the structure. There were few time-consuming hand-fitted machine components. Inside the engine bay, Schmidt noticed broad clearances around moving parts where dust could enter without immediate seizure. The engine itself had a blunt, obvious geometry, a low compression design that tolerated poor fuel and minimal maintenance rather than relying on fine-tuned performance. In his notebook, later paraphrased in reports, Schmidt listed what he saw with an engineer's bluntness. Construction appears careless, yet there is consistency in simplification. Components repeated, dimensions rough but standardized. Those notes read like a litany of small puzzles. He found brackets whose holes lined up with identical holes on other structures, fasteners that seemed to recur in different assemblies, a carburetor whose casting matched the dimensions of others with only minor differences. It was as if the half-track had been designed under a different question. Not, how do we make this vehicle exceptional, but how do we make this vehicle interchangeable with thousands more? The engine bay yielded more than the obvious. The fuel pump and the carburetor had tolerances that, by German standards, were wide. Where German engines asked for refined gasoline and meticulous tuning, this American motor would run on lower-octane fuel and live through weeks of grit and neglect. Schmidt ran his fingers along manifold flanges and found gasket surfaces that might leak on a fine machine but would be simple to reseat or replace in the field. He noted, reported rather than sworn, that these were not accidental shortcuts, but choices oriented toward the realities of a global war fought by conscripted crews moving across wide deserts and muddy Italian roads. The repair manual tucked beneath the dashboard made the pattern explicit. It was thin, heavily illustrated, and startlingly plain. Pictures of components, arrows, short steps, remove, replace, tighten. There were simple diagrams for removing a wheel hub, replacing a water pump, clearing a carburetor. The language assumed limited technical training. The illustrations were drawings, not photographs, clean, schematic, and aimed at action rather than theory. Schmidt wrote later that the manual read like instructions for a machine meant to be fixed by a farmhand with a wrench and a day's patience, not a craftsman with a lathe. A few yards away, Fritz Keller opened a crate that had been piled with spare parts. He laid them on a tarp, dozens of identical carburetor housings, stacks of bolts sorted into piles, matched brake linings, and standard filters. It was not the careful assortment of unique pieces, but the type of redundancy that turns a factory's output into an army's resilience. Keller ran his hand across the row of carburetors, stamped tags, matching part numbers stamped in rough sequence, and said something that Schmidt later paraphrased as, "One part fits many mouths." The phrase was simple, but the implication struck hard. One factory line could feed many machines. One spare crate could return many vehicles to service. That crate and the spare parts strewn on the tarp were tactile proof of a systems mindset. Interchangeability meant logistics suddenly ceased to be a menu of unique fixes and became a matter of supply lines and crates.
If a brigade could carry standardized spare parts, its vehicles could be repaired quickly by any crew with a basic manual. If a part would fit variants of trucks, half-tracks, and artillery tractors, the factory's output gained leverage across the whole force. The true value was not in any single vehicle's elegance, but in the predictability and reach of the supporting infrastructure. This is where the German and American philosophies diverged. German engineering, at least in its pre-war and interwar peacetime ideal, prized refinement.
Precision machining, tight fits, and carefully engineered systems produced machines that performed exceptionally when serviced by skilled personnel. But that model demanded skilled labor, careful assembly, and a dense web of suppliers. It assumed a stationary production rhythm and a culture that tolerated the cost of time and specialization. American wartime production asked a different set of questions. Factories were retooled to emphasize speed and repeatability. Stampings, castings, parts designed to be produced quickly in large numbers. The design choices accepted performance trade-offs in exchange for uniformity and the ability to put simple hands on common tools. The diagrams in the manual reflected that approach. Training prioritized familiarity and quick fixes, not the deep apprenticeship of European workshops. In effect, the United States treated vehicles as components of an industrial ecosystem where scale and replacement were strategic weapons in themselves. Schmidt began to do arithmetic in his head and in his notebook, not to generate precise wartime statistics, but to frame the problem. He and his colleagues estimated the time required to strip, repair, or reassemble common American components versus what it took to service typical German armor. The half-track, by reported estimates he wrote down, could be readied or repaired in a matter of hours. A Panzer required days of attention, specialized parts, and skilled crews. The numbers themselves were approximations, but the ratio mattered more than any figure. Short repair times multiplied across thousands of machines created a tempo of replacement and sustainment German industry struggled to match. The material evidence supported this conclusion. Schmidt found the same bolt size recurring across different assemblies. He traced part numbers and stamping codes and saw the logic of interchangeability writ in metal. The casting marks showed molds reused for multiple components. Where a German workshop might fashion a bearing seat to precise specs, the American design used a standard sleeve that could be swapped without custom fitting. The functional effect was that American units could operate at a different logistical tempo. Instead of patching unique machines, they replaced known quantities. This tempo had battlefield consequences that were strategic rather than tactical. Losses in combat are inevitable. The decisive question is how an army turns losses into opportunities to maintain pressure. A nation that can replace armored cars, trucks, engines, and parts at scale can tolerate higher attrition and keep pushing. Schmidt's field notes, reported and later summarized in internal dispatches, convey the dawning realization. Tactical victories matter, but attrition economies and production rhythms shape campaigns. Standing at that lamplit engine bay, he understood he was not just measuring metal, he was reading a nation's answer to the problem of sustaining war.
That recognition precipitated a grim clarity about German constraints. Germany had craftsmanship and concentrated industrial skill, but by 1944, those resources were strained. Skilled labor was scarce, suppliers were dispersed and vulnerable to bombing, and the culture of precision made standardization and mass interchangeability harder to implement rapidly. German supply chains often relied on specialized parts sourced from particular vendors. That model created brittle dependencies. In contrast, American industry leaned toward broad standardization from the outset, commoditized parts, simplified assemblies, and production lines oriented around speed and interchangeability. The effect was not a moral failing, but an industrial mismatch adapted to different strategic questions. It is important to stress what this argument is not. The discovery in the half-track does not prove that American machines were superior in every performance metric. On many measures of engineering refinement, German machines could be more efficient, powerful, or durable when finely tuned and carefully maintained. What the half-track revealed was not a superiority of craft, but a different doctrine. Design for maintenance, design for replacement, and the deliberate lowering of performance thresholds to gain resilience. The Americans accepted a degree of technical compromise because they value predictability at scale. The tactical implications show up in simple scenes. A convoy stalled on a muddy road could be cleared faster if spare wheel hubs and drive assemblies were common and available. Field units with a trunk of standardized spares could perform a roadside swap in hours, returning vehicles to circulation. Meanwhile, a damaged German tank with unique precision-made parts could remain out of action for days, tied to the availability of a specialized workshop and skilled technicians. The cumulative effect of these small delays, vehicle by vehicle, day by day, shifts operational momentum. Schmidt's notebook recorded not as rhetoric but as observation that the American approach assumed crews would be inexperienced, that vehicles would be driven hard, and that parts would be lost. Design choices, training briefs, and logistical planning all absorbed that assumption. The manual's images and the spare crate's contents were evidence. The system assumed failure and built redundancy into supply and design. That assumption, once converted into factories churning parts and into trains moving spares to the front, made a difference no single masterpiece could match. Fritz Keller's role in the workshop that afternoon illustrates the human dimension of an industrial logic. Keller was not a philosopher of systems. He was a mechanic who knew the feel of a part. When he picked up a stamped recoil plate and fitted it into a chassis, the fit was forgiving. He could secure it with a common wrench. The ease of that gesture was itself a strategic lever.
The labor to effect repairs did not require absolute expertise. It required repetition and standard procedures. In a nation mobilized for industrial scale, repetition is not banal, it is powerful. From the mud of Anzio, the broader picture unfolded. America's secret was not a single technological trick hidden in the half-track. It was an organizational and conceptual choice embedded in design. Prioritize interchangeability, tolerate looser tolerances where appropriate, and design manuals and training that converted a population into a vast, replaceable maintenance workforce. The vehicle was merely a node in a network, factories producing identical parts, railroads moving crates, supply depots stocking standardized spares, training programs churning out operators who could follow schematic diagrams. The half-track simplicity was a reflection of an industrial ecosystem rather than an end in itself. Schmidt's realization was both technical and strategic. Technical because he could point to bolts, castings, and carburetor housings. Strategic because those components aggregated into a wartime advantage. He concluded, not as a moral judgment but as an engineer, that engineering brilliance concentrated into a few excellent machines cannot substitute for a systematic capacity to field, fix, and replace. He reported this not as a flourish, but as the most practical explanation for why, on the battlefield, momentum sometimes mattered more than individual technical superiority. That insight reframes common narratives about wartime technology. It suggests that victory in industrialized conflict often hinges less on singular genius and more on the interaction between design, production, training, and logistics. A nation that builds machines as part of a predictable, scalable system can sustain operations under attrition in ways that a nation focused on artisanal excellence cannot. In other words, systems thinking beats isolated technical mastery when the decisive variable is scale and continuity. The field evidence in the half-track remains useful as a teaching tool. A carburetor stamped identically in dozens of crates, a manual with simple diagrams, bolts of the same head found across multiple assemblies. These details are the micro-evidence that let an engineer like Schmidt see the macro pattern. Good historical analysis always ties broad claims to material traces, and here the traces are literal: metal, paper, and patterns of manufacture. What does this lesson mean today? The wartime lesson is not obsolete. Modern militaries and industries still face choices between bespoke excellence and scalable interchangeability. The balance is always contextual. There are domains where precision and specialization remain essential, but the Anzio half-track reminds us that survivability and sustainability are design goals as important as peak performance.
In contemporary supply chains, in commercial product design, in any tech competition where production and maintenance matter, the same principle applies. The ability to produce and sustain at scale alters competitive landscapes. The half-track itself did not win the war. It was neither glamorous nor singularly decisive, but under that bare lamp, German engineers found a strategic truth. America's secret was not an inscrutable technology hidden beneath panels. It was an industrial doctrine that accepted imperfection where it mattered, standardized the replaceable, and built logistics and training to turn factories into persistent combat power. That doctrine turned spare parts into strategic depth and made momentum, continuous, replaceable, repairable, into a weapon as real as armor or guns. On the evening of March 18th, as the field workshop wound down, the half-track was stripped of useful components, photographed, noted, and somewhere along the chain of command, summarized into a report that would be read by others who knew how to translate metal into strategy. Schmidt's notes were careful, his language pragmatic. He did not pronounce destinies. He recorded evidence and drew the conclusion that systems matter. That measured observation is the heart of what was found under the lamp, a lesson about scale, redundancy, and the quiet power of being able to replace what you lose. If this examination resonates with you, stay with the rest of the series. There are more episodes that trace how industrial decisions turned into strategic outcomes. The half-track is a small object with a large lesson. When war is decided by volume and continuity, the factories and the manuals behind the machines can be the decisive actors. For a deeper dive into how production rhythms shaped campaigns in 1944 and beyond, check the description for sources and related material.